Have you ever looked up at the night sky and wondered what most of it is made of? Or why the universe is expanding faster and faster into darkness? Tonight, we're beginning a journey through 100 levels of cosmic mystery, from the invisible forces that shape galaxies to the nature of consciousness itself. Welcome to Midnight Science. This channel is dedicated to the art of falling asleep while falling deeper into wonder. Each level takes you further into the strange, beautiful architecture of existence, at a pace designed for late-night contemplation and peaceful drift. I'd love to know where you're listening from and what brought you here tonight. Are you under clear skies or city lights? Drifting off in silence or with rain tapping at your window? Drop a comment and let me know. It's always humbling to see how far these nocturnal explorations travel. If you find comfort in cosmic questions, please consider giving this video a like and subscribing. It helps this corner of the universe grow, one sleepy mind at a time. And to those already here, thank you. You're the reason these journeys continue. Don't forget to tap the notification bell so you won't miss the next descent through space, time, and the mysteries they contain. Hopefully, this won't be too interesting to keep you awake. But if it is, at least you'll drift off somewhere along this climb through cosmic ideas, each one a little stranger than the last, learning as you let go. Because once you start asking the right questions, the universe stops being background noise and becomes the most fascinating story ever told. Now, close your eyes, settle in, and picture the universe. You might see stars scattered like salt across black velvet, galaxies spinning in the dark, planets orbiting distant suns, all of it glowing, shining, announcing its presence across the void. But here's the thing, almost none of it is there. Not in the way you think. The universe you imagine, the one made of light and matter, and everything you've ever seen or touched or known, accounts for roughly 5% of everything that exists. 5%. The rest is something else entirely. We call it dark matter and dark energy, though those names are more confession than description. We name the unknown after what it isn't. Dark because it doesn't shine. Matter and energy because we don't know what else to call them. Welcome to Level 1, the weight of the invisible. In the 1930s, an astronomer named Fritz Zwicky was studying galaxy clusters, watching how they moved, how they held together. He measured their mass based on the light they gave off, then measured their motion to see if the numbers matched. They didn't. The galaxies were spinning far too fast. At those speeds, they should have torn themselves apart, flung their stars into the void like water off a spinning wheel. But they didn't. Something was holding them together, something with mass, something with gravity, something invisible. Zwicky called it dark matter, and for decades, no one believed him. Then we kept looking. We watched galaxies rotate, their outer edges moving just as fast as their centers, defying every law we understood. We studied galaxy clusters and saw the same impossible motion. We pointed our telescopes at distant starlight and watched it bend around invisible mass, curved by gravity we couldn't see. The light was telling us the truth. There was something there, a scaffold, a skeleton made of shadow. We still don't know what it is. It doesn't emit light. It doesn't absorb light. It doesn't interact with ordinary matter in any way we can detect, except through gravity. It passes through you, through me, through the Earth itself, billions of particles every second, and we feel nothing. Most of reality is a ghost. But here's what unsettles me most. It isn't rare. Dark matter isn't some exotic substance hiding in the corners of the cosmos. It's the foundation. There's 5 times more dark matter than ordinary matter, 5 times more invisible than visible. The stars and planets and everything we've ever known are the minority, the exception. We are made of the rare stuff, so when you look up at the night sky, remember this. The darkness between the stars isn't empty. It's full. It's the universe showing you its true face. A face made mostly of things we cannot see, cannot touch, cannot understand. And it gets stranger. Because while dark matter holds the universe together, something else is tearing it apart. In the late 1990s, astronomers were measuring distant supernovae, using them as cosmic mile markers to map the expansion of the universe. Everyone expected the same result. The universe was expanding, yes, but gravity should be slowing it down. The mutual attraction of all matter should act like a brake, gradually reducing the speed of expansion. But that's not what they found. The universe wasn't slowing down. It was speeding up. Distant galaxies weren't just moving away from us. They were accelerating, moving faster and faster, as if something was pushing them, stretching the fabric of space itself with every passing moment. We call this dark energy. Though the name is just as helpless as before, no one knows what it is. Some think it's a property of space itself, a kind of inherent tension woven into the vacuum. The cosmological constant, Einstein called it, though he abandoned the idea, calling it his greatest blunder. Turns out he might have been right the first time. Others think it's a field, something dynamic, changing over time, pushing against gravity in ways we're only beginning to measure. But here's the most unsettling possibility. What if it's not a force at all? What if this acceleration is simply the nature of nothingness itself? What if empty space has weight, has pressure, has a kind of anti-gravity baked into its very existence? What if the universe isn't being pushed apart by something, but rather pulled apart by nothing? By the time you finish reading this sentence, space will have stretched a little more. By the time you fall asleep tonight, the universe will be larger than it was when you woke this morning, and the galaxies we see now, the ones glowing at the edge of our vision, will one day be so far away that their light will never reach us. They'll cross a horizon we can't follow, disappearing not because they died, but because the universe grew too large to hold them in view. One day, in the deep future, a civilization might look up at the sky and see almost nothing, a handful of nearby galaxies, and beyond that, darkness. They might conclude they live in a small, lonely universe. They might never know how wrong they are. We're lucky. We live in an age where we can still see the cosmos in its full complexity, still catch the light of distant galaxies before they slip beyond our reach. But we're also living in a mystery. Let's take inventory. Ordinary matter, the stuff of stars and planets and you and me, makes up about 5% of the universe. Dark matter, invisible but massive, accounts for about 27%. Dark energy, the force or field or property of space driving the acceleration, makes up the remaining 68%. We know almost nothing about 95% of reality. Think about that. We've mapped the human genome, we've split the atom, we've sent machines to the edge of the solar system and peered back to the first moments after the Big Bang. We've built cities and written symphonies and decoded the mathematics of black holes. And yet, we inhabit a sliver of the cosmic truth. The universe we see, the one we study and celebrate and navigate, is a thin skin on the surface of something far stranger. We're like sailors on an ancient map, hugging the coastline, afraid to venture into the blank spaces where the cartographers wrote, "Here be dragons." Except the dragons are real, they're just invisible. This is level 10, the cosmic puzzle pieces. Everything we know fits together into a picture, but we're missing most of the pieces. Dark matter holds galaxies in place. Dark energy pushes them apart. Ordinary matter glows in the space between, a brief flicker of light in an ocean of shadow. And we stand here, on this small world, trying to understand it all, trying to see the invisible, trying to name the unknown. It's humbling, isn't it? To realize that we're not just small in size, but small in comprehension. That the universe isn't just larger than we imagined, but stranger. That the questions we thought we'd answered have only opened the door to deeper mysteries. And yet, there's something beautiful in that. Because mystery isn't the enemy of knowledge, it's the engine. Every answer we find reveals a dozen new questions. Every layer we peel back shows us another beneath it. The universe isn't a puzzle to be solved and set aside. It's an infinite conversation, and we've only just begun to listen. So here we are at the threshold. We've learned that most of reality is invisible, that the universe is expanding faster and faster into a future we can't predict, that everything we know is a small island in a vast, dark sea. And now the question becomes, if the universe hides most of itself, What else is it not telling us? There's a light that fills the universe. You can't see it with your eyes. It's too faint, too cold, stretched too thin across the vastness of space. But it's there, everywhere. In every direction you look, in every empty patch of sky, there's a gentle glow washing over everything, a whisper from the past. We call it the cosmic microwave background, the CMB, and it's the oldest light in the universe. Imagine you could see it. Imagine the sky lit up not with stars, but with this uniform, soft radiation. It would look almost perfectly smooth, almost perfectly even. A canvas of ancient light painted across the entire cosmos. This is the afterglow of creation. 13.8 billion years ago, the universe was born. Not in a place because there was no place yet. Not at a time because time itself was just beginning. Everything that exists, everything that ever will exist, was compressed into something smaller than an atom, hotter than anything we can imagine, denser than the core of a collapsing star. And then it expanded. Not into space. Space itself expanded. The universe didn't explode into emptiness. The universe was the explosion. Every point moving away from every other point. The fabric of reality stretching in all directions at once. For the first 380,000 years, the universe was opaque. A fog of plasma, particles colliding, light scattering endlessly. You couldn't see through it. Nothing could. But then the universe cooled. Electrons and protons joined together to form the first atoms. Mostly hydrogen, some helium, and suddenly, for the first time, light could travel freely. It was released, sent outward in all directions, carrying with it a snapshot of what the universe looked like in that moment. That light has been traveling ever since. As the universe expanded, the light stretched with it. What was once visible light, glowing hot and bright, cooled into infrared, then into microwaves. The fire of creation dimmed to a whisper. But it never went away. In 1964, two scientists at Bell Labs were trying to eliminate static from a radio antenna. No matter what they did, they couldn't get rid of it. A persistent hum coming from everywhere at once. They checked the equipment. They cleaned out pigeon droppings. They pointed the antenna in every direction. The hum remained. Eventually, they realized what they were hearing. It wasn't noise. It was the universe itself, still glowing from its birth. They'd discovered the cosmic microwave background, the afterglow of the Big Bang, and with it, they'd given us a map, a photograph of the infant universe, taken when it was only 380,000 years old. When we study this light today, we see something remarkable. It's almost perfectly uniform, almost perfectly smooth. The temperature varies by only a few millionths of a degree from one part of the sky to another. Tiny ripples, barely there, like the surface of a perfectly still pond, disturbed by the faintest breeze. But here's the mystery. The universe was enormous by then. Light from one edge of the observable universe couldn't have reached the other edge yet. There hadn't been enough time. So, how did opposite sides of the cosmos know to be the same temperature? How did the universe coordinate itself into this impossible smoothness? The answer takes us back even further, to the first fraction of a second after the Big Bang, to a moment we call inflation. Imagine the universe as a seed, smaller than anything you can picture, and then, in less time than it takes light to cross an atom, that seed exploded. Not gradually, not slowly, faster than light itself. In a tiny sliver of a second, perhaps as brief as 10 to the negative 32 seconds, the universe expanded by a factor of at least 10 to the 26. That's a 1 followed by 26 zeros. Space itself stretched, ballooned, inflated like a sphere blown up to impossible size. This is cosmic inflation. Before inflation, the universe was small enough that every part could be in contact, could reach thermal equilibrium, could settle into the same temperature. Then inflation kicked in, blowing that tiny, smooth patch up to cosmic scales, carrying that smoothness with it. By the time inflation ended, the universe was smooth, flat, uniform, The wrinkles had been stretched out, the irregularities ironed away. What had been a chaotic quantum foam was suddenly calm, vast, ready to begin the long journey toward galaxies and stars. But not perfectly smooth, because quantum mechanics doesn't allow perfection. At the smallest scales, reality trembles. The quantum vacuum isn't empty. It's filled with fluctuations, tiny variations in energy, particles popping in and out of existence in the span of a heartbeat. Normally, these fluctuations are so small they don't matter. But during inflation, something extraordinary happened. Those quantum ripples were stretched, inflated along with space itself, blown up from subatomic scales to cosmic scales. And when inflation ended, those ripples froze in place. Tiny variations in density spread across the universe. Regions that were just a little bit more dense, regions that were just a little bit less. And those tiny differences mattered because gravity amplifies. Denser regions pulled in more matter. They grew. Over millions of years, those ripples became seeds. Seeds that grew into galaxies, into clusters, into the cosmic web we see today. Every galaxy began as a quantum fluctuation. Every star, every planet, every living thing. All of it traces back to that first moment, to the instant when inflation stretched the universe and carried those quantum whispers into the fabric of space itself. We are the children of quantum noise. But this raises a question. What caused inflation? We don't know. There are theories, models, mathematical frameworks that work beautifully. We think it was driven by a field, something like the Higgs field, filling space with energy and then decaying, releasing that energy into matter and radiation. We call it the inflaton field, though that's just a name we give to our ignorance. The mathematics works. The predictions match what we observe. But we don't know what the inflaton is. We don't know why it existed. We don't know what triggered it to begin or what caused it to stop. We just know it happened. And that brings us to the edge, to the deepest question of all: what came before inflation, before the Big Bang, before the universe itself? What was there? This is where science meets silence, because the word before might not even make sense. Time, as we understand it, began with the Big Bang. Space and time are woven together, part of the same fabric. If the universe had a beginning, then time had a beginning. And if time had a beginning, then asking what came before is like asking what's north of the North Pole. The question contains its own impossibility. And yet, we ask it anyway, because we can't help ourselves. Some physicists think the Big Bang wasn't the beginning. They propose a cyclic universe, one that expands and contracts in an eternal rhythm. The Big Bang was just the latest bounce, the moment when a previous universe collapsed and rebounded into ours. Before our universe, there was another, and before that, another. An infinite chain stretching backward and forward, each cycle creating and destroying itself in turn. Others imagine a multiverse, not just many universes existing side by side, but universes branching off from quantum events, or budding off from colliding membranes in higher dimensions. In these models, our Big Bang was just one event among countless others. Our universe is a bubble in an infinite foam, each bubble with its own laws, its own constants, its own story. Or maybe there's something stranger. Maybe the universe created itself. In quantum mechanics, particles can tunnel through barriers they shouldn't be able to cross. Entire systems can borrow energy from the vacuum as long as they pay it back quickly enough. Some theories suggest the universe did the same thing, that it tunneled into existence from nothing, a quantum fluctuation that didn't collapse back into the void, but instead inflated into reality, a universe from nothing. Or perhaps the question is wrong. Perhaps asking what came before the Big Bang is like asking what happens when an unstoppable force meets an immovable object, a paradox built on false assumptions. Perhaps the universe simply is, has always been in some sense, will always be. Perhaps causality, the chain of cause and effect we rely on, breaks down at the boundary of existence. Perhaps the beginning has no beginning. We don't know. And there's something humbling about that. For all our telescopes and equations, for all our satellites mapping the cosmic microwave background, and our detectors searching for gravitational waves, we stand at the edge of knowledge and look out at a horizon we cannot cross. We can trace the universe back to a fraction of a second after its birth. We can measure the afterglow of creation. We can map the seeds of galaxies and the infant cosmos. We can calculate how inflation stretched space and smoothed the universe into the form we see today. But the first moment, the spark that lit the fire, that remains beyond us. And maybe it always will. Or maybe not. Because we're still looking, still searching, still asking. Humanity has a way of finding answers to questions that once seemed unanswerable. We've gone from wondering if the stars were holes in a celestial sphere to measuring the expansion rate of the universe. We've gone from myths about creation to equations that describe the first moments of time. Who's to say we won't go further? Who's to say the boundary we see today won't be crossed tomorrow? The universe has already shown us that it's stranger than we imagined. Dark matter, dark energy, cosmic inflation, quantum fluctuations becoming galaxies. Every answer has been a doorway to something deeper, something more profound. And the story isn't over, because to understand beginnings, we must look for other forms of life. Not just biological life, though that matters too, but cosmic life, the birth of stars, the formation of planets, the cycles that turn hydrogen into helium, dust into worlds, chaos into order. The universe creates, over and over, in a million different ways, and we're about to explore what that means. The Milky Way is ancient, 13 billion years old, give or take. 400 billion stars, maybe more. Countless planets orbiting those stars, worlds of ice and rock and gas spinning through the darkness. And as far as we can tell, it's silent. No signals, no transmissions, no evidence of anyone else looking back. This is the Fermi paradox, and it haunts us. The physicist Enrico Fermi asked a simple question over lunch one day in 1950. If intelligent life is common in the universe, if civilizations arise naturally, given enough time and the right conditions, then where is everyone? The numbers suggest we shouldn't be alone. Our galaxy is vast, but it's also old. Life on Earth took 4 billion years to evolve from single cells to beings capable of asking questions about the cosmos. 4 billion years sounds like a long time, but the galaxy is 3 times older than that. If Earth isn't special, if life follows the same basic chemistry everywhere, then there should be civilizations out there that are billions of years ahead of us. Civilizations that have had enough time to spread across the galaxy, to build structures we could see, to send signals we could detect. And yet, we see nothing. We've listened to the stars with radio telescopes, searching for patterns in the noise. We've scanned the sky for anomalies, for megastructures, for signs of engineering on planetary scales. We've looked for laser pulses, for industrial pollution in distant atmospheres, for anything that might suggest intelligence. The universe remains quiet. Why? Maybe life is rare. Maybe the jump from chemistry to biology requires such a precise set of conditions that Earth is one of a handful of lucky accidents in the entire galaxy. Maybe the universe is full of sterile worlds, beautiful but lifeless, waiting for something that will never come. Or maybe life is common, but intelligence isn't. Earth has been alive for billions of years, but only in the last few million has anything resembling intelligence emerged. And only in the last century have we become technological, capable of sending signals into space, capable of listening. What if that's the bottleneck? What if the galaxy is teeming with microbes, with simple organisms clinging to rocks and floating in alien seas, but intelligence is vanishingly rare? What if consciousness is the fluke, not life itself? Or maybe civilizations don't last. Maybe intelligence carries with it the seeds of its own destruction. War, climate collapse, resource depletion, artificial intelligence run amok. Perhaps every civilization reaches a point where it either transcends its origins or destroys itself, and the window where they're visible to others is heartbreakingly brief. 1,000 years of radio signals in a galaxy billions of years old. A candle flickering in an endless night. Or maybe they're out there and we just haven't noticed. Maybe they're so advanced that their technology looks like nature to us. Maybe they communicate in ways we can't detect, using physics we haven't discovered. Maybe they're deliberately quiet, hiding, waiting, watching to see if we're worth talking to. Or maybe they're all around us and we're too young to see. There's something deeply unsettling about the silence, because it means one of two things. Either we're alone, the only conscious beings in a galaxy of empty worlds, standing in a universe that has no idea we exist, or we're surrounded, and something prevents civilizations from making themselves known. Both possibilities are terrifying in their own way. But while we search for intelligent life, we've found something else. Worlds, thousands of them. For most of human history, we knew of only the planets in our own solar system. 8 worlds, a handful of moons, and the distant promise that maybe, somewhere, other stars had planets too. Then, in 1995, we found the first exoplanet orbiting a sun-like star. And the floodgates opened. Today we've confirmed more than 5,000 exoplanets, worlds orbiting other stars, and we've only just begun. Every new telescope reveals more. Every new technique finds planets we couldn't see before. The galaxy is a garden, and it's more diverse than we ever imagined. There are planets larger than Jupiter, gas giants orbiting so close to their stars that their atmospheres are being stripped away, trailing behind them like comet tails. Hot Jupiters, we call them, worlds where the temperature exceeds 1,000 degrees, where metals vaporize and winds scream at thousands of miles per hour. There are planets that rain glass sideways, where silicate particles condense in the upper atmosphere and fall through winds faster than the speed of sound. There are worlds where it rains molten iron, planets covered in oceans with no land in sight, water worlds where the pressure at the ocean floor is so intense it forms exotic types of ice, hot ice, compressed into crystalline structures that shouldn't exist. There are rogue planets, ejected from their solar systems, wandering the galaxy alone in the dark. Worlds with no star to warm them, frozen, lifeless, drifting through the void for billions of years. And then there are the ones we care about most, the Earth-like worlds, planets orbiting in the habitable zone, that narrow band of space where water can exist as a liquid. Not too close to the star, not too far. Just right. We call it the Goldilocks zone, and we've found dozens of planets there. Rocky worlds, similar in size to Earth, orbiting red dwarf stars or sun-like stars, bathed in light that could support oceans, atmospheres, maybe even life. We don't know yet if any of them are truly like Earth. We can measure their size, their mass, their distance from their star, but their surfaces remain mysteries. Are they covered in water? Do they have continents? Atmospheres thick with clouds, or thin wisps of gas barely clinging to the surface? We're building telescopes to find out. Instruments that can analyze the light passing through an exoplanet's atmosphere, looking for the chemical signatures of life. Oxygen, methane, combinations of gases that don't make sense unless something is producing them. Biosignatures. And maybe, one day soon, we'll find them. But even if we don't find life on those distant worlds, we've found it in the strangest places here at home. Life on Earth is more resilient than we ever thought possible. We've found microbes living miles beneath the ocean floor in solid rock, surviving on chemical energy in places where sunlight has never reached. We've found them in the scalding water of hydrothermal vents, where temperatures exceed boiling and the pressure would crush a submarine. Entire ecosystems thriving in conditions that should be lethal. We've found life in the frozen deserts of Antarctica, in lakes buried beneath miles of ice, untouched by the outside world for millions of years. Organisms that survive by metabolizing sulfur, by feeding on minerals, by finding energy in places we thought were barren. We've found extremophiles that can survive the vacuum of space, organisms that can endure radiation, doses that would kill anything else, bacteria, that go dormant for thousands of years and wake up when conditions improve. Life, it turns out, doesn't need much. It needs liquid water, or something like it. It needs a source of energy. It needs the right chemistry. But beyond that, it's adaptable, creative, tenacious. If life can thrive in Earth's most extreme environments, what could it do elsewhere? On Mars, where ancient river valleys suggest there was once liquid water on the surface, where subsurface ice might still harbor microbes, frozen, waiting. On Europa, one of Jupiter's moons, where an ocean of liquid water lies beneath a thick shell of ice, an ocean kept warm by tidal forces, by the constant flexing of the moon as Jupiter's gravity pulls and releases. An ocean that might be home to life, forms we can't even imagine. On Enceladus, Saturn's tiny moon, where geysers erupt from the South Pole, spraying water vapor and organic molecules into space. A subsurface ocean connected to a rocky core, a place where chemistry and heat and water come together in the darkness. On Titan, Saturn's largest moon, where lakes of liquid methane and ethane pool on the surface, where organic chemistry happens at temperatures far below freezing. A world so alien that life there, if it exists, might not even be based on water, might use methane instead, might be something we wouldn't recognize. The possibilities are staggering, but they're also humbling. Because if life exists out there, if we find even a single microbe on Mars or Europa or in the clouds of Venus, it changes everything. It means life isn't rare. It means the universe is alive in ways we're only beginning to understand. And if life is common, then the Fermi paradox becomes even more pressing. Where is everyone? Maybe intelligence is the rare thing. Maybe the galaxy is full of microbes and algae and simple organisms. But consciousness almost never happens. Maybe we're surrounded by life, but alone in awareness. Or maybe we're not looking in the right way. Maybe intelligence doesn't stay biological. Maybe every civilization reaches a point where it merges with its technology, becomes something we wouldn't recognize as life. Maybe they've moved beyond physical form, beyond the need for planets and stars. Maybe they're still here, but we're like ants trying to understand the internet. Or maybe the answer is simpler. Maybe the universe is vast enough that even a galaxy full of civilizations would seem empty. Space is so large, time is so long, that two civilizations might exist light years apart and never overlap, never intersect, never know the other was there, ships passing in an infinite night. We don't know, but we keep looking, because the question matters. Are we alone or surrounded? And what does it mean for us if the answer is either? If we're alone, then we carry a profound responsibility. We might be the only consciousness the universe has ever produced, the only beings capable of understanding it, of appreciating it, of giving it meaning. If we're surrounded, then we have to ask why we haven't met anyone yet. What are we missing? What are they waiting for? And what does it say about the future of any civilization that reaches for the stars? Both answers change who we are. Both answers demand that we think carefully about what comes next. Because life, or its absence, forces another question. What becomes of the universe's deepest secrets when nothing conscious remains to witness them? There are places in the universe where the rules break down, where space curves so severely that it folds in on itself, where time slows, stops, becomes meaningless, where light itself cannot escape. We call them black holes, and they are the darkest objects in existence. Not dark because they lack light, though they do. Dark because they consume it. Dark because they represent a boundary beyond which nothing, not even information itself, can return. Or so we thought. For decades, black holes seemed straightforward, at least in principle. A massive star reaches the end of its life, exhausts its fuel, and collapses under its own gravity. The core compresses, smaller and smaller, denser and denser, until it crosses a threshold, the Schwarzschild radius, the point of no return. Once something crosses that boundary, the event horizon, it's gone, pulled inexorably toward the singularity at the center, where density becomes infinite and the equations of physics break down into meaninglessness. Einstein predicted them. Schwarzschild found the mathematical solution. And for a long time, that was enough. But then Stephen Hawking asked a question. If black holes can only grow, only consume, never give anything back, what happens to all the information that falls in? Information in physics isn't just data. It's not files on a computer or words in a book. It's the complete quantum state of every particle, every field, every piece of matter and energy in the universe, the fundamental description of what something is. And according to quantum mechanics, information cannot be destroyed. It can be scrambled. It can be encoded in ways that make it unreadable. But it has to exist somewhere, in some form, always. This is a bedrock principle, one of the deepest laws we know. But black holes seem to violate it. Hawking realized something remarkable in the 1970s. Black holes aren't entirely black. They emit radiation, not from inside the event horizon, but from just outside it, where quantum effects allow particle-antiparticle pairs to form from the vacuum. Normally, these pairs annihilate immediately, but near a black hole, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is radiating. Hawking radiation. And here's the crucial part. This radiation carries energy. Very slowly, over unimaginable timescales, black holes evaporate. They lose mass. They shrink. Eventually, after a time span that makes the current age of the universe look like an eye blink, they disappear entirely. But the radiation that escapes is thermal, random. It doesn't carry information about what fell in. It's like burning a book and studying the smoke. You can measure the heat, the light, the chemistry of the gases, but you can't reconstruct the words. So, where does the information go? If it falls into the black hole and the black hole evaporates and the radiation contains no trace of what was lost, then information has been destroyed, and that's impossible. This is Hawking's paradox, and for decades, it tore at the foundations of physics. Some physicists said the information must be preserved somehow, encoded in the radiation in ways we don't yet understand. Others said maybe quantum mechanics needs to be revised. Maybe information can be destroyed under extreme conditions. Hawking himself eventually changed his mind. He came to believe that information does escape, but in such a scrambled form that it's effectively irretrievable, like a shredded document mixed with a million others. But even that left questions. How does the information escape? Where is it stored while the black hole exists? And what does it mean for our understanding of reality if a black hole can encode everything that falls into it on its surface? That last question led to one of the strangest ideas in modern physics, the holographic principle. Imagine a black hole's event horizon, a spherical boundary surrounding the singularity, marking the point of no return. Now imagine that everything inside the black hole, all the information about everything that ever fell in, is encoded on that surface. Not inside, on the surface, like a hologram, where a two-dimensional film contains all the information needed to reconstruct a three-dimensional image. The event horizon becomes a cosmic library. Every particle, every atom, every piece of matter that crossed the boundary leaves an imprint, and that imprint contains its complete quantum state. This isn't just a metaphor. The mathematics suggests that the maximum amount of information a region of space can contain is proportional to the area of its boundary, not its volume. It's as if three-dimensional space is an illusion, a projection, and the true reality is encoded on a two-dimensional surface. We live inside the hologram, and black holes, the most extreme objects in the universe, are the places where this truth becomes unavoidable. If this is correct, if information really is stored on the event horizon, then nothing is truly lost when something falls into a black hole. It's scrambled, encoded in ways we can barely comprehend, but it's there. The universe keeps its books balanced. But this raises another question, darker and more unsettling. What happens to someone who falls in? From the outside, they slow down as they approach the event horizon. Time dilation stretches every second into eternity. They grow dimmer, redder, until they fade from view, frozen at the boundary forever. But from their perspective, nothing special happens at the horizon. They cross it smoothly, unaware that they've passed the point of no return. They fall toward the singularity, time passing normally until tidal forces rip them apart. This is the classical picture. But if information is encoded on the horizon, then the infalling observer must interact with it. They must leave their imprint. And that interaction might not be gentle. Some physicists argue there's a firewall at the event horizon, a sheet of high-energy particles, a quantum inferno that incinerates anything trying to cross. The price of preserving information. The observer doesn't fall peacefully into darkness, they burn. Others say this can't be right. General relativity demands that space near the horizon is smooth, empty, unremarkable. An observer should cross without noticing. The firewall would violate this principle, would tear apart the equivalence between gravity and acceleration that Einstein held sacred. So, which is it? Does the traveler burn or drift peacefully into mystery? We don't know. The universe refuses a single answer, because the paradox cuts deeper than black holes. It's about the nature of reality itself. If the holographic principle is correct, then the universe we see, the three-dimensional space we move through, might be a projection from a lower dimensional boundary. Everything we experience, every particle, every force, every moment of time, might be encoded on some distant surface. We might be shadows on a wall, and black holes are where the shadows break down, where the projection flickers, where the underlying structure of reality becomes visible. This is what happens at the edge of oblivion, not just the destruction of matter, but the collision of our two deepest theories, general relativity, which describes gravity and the curvature of space-time, and quantum mechanics, which describes the behavior of particles and fields. Both theories are incredibly successful. Both make predictions that match experiments to absurd precision, but they contradict each other at the event horizon. General relativity says space is smooth. Quantum mechanics says information must be preserved. You can't have both, not without something new, something we haven't discovered yet, a theory of quantum gravity. This is what physicists are searching for, a framework that unifies relativity and quantum mechanics, that describes what happens when gravity becomes strong enough that quantum effects matter, when space-time itself becomes granular, uncertain, subject to the strange rules that govern the subatomic world. String theory is one attempt. It proposes that particles aren't points, but tiny vibrating strings, and that the universe has more dimensions than we can see, curled up so small we can't detect them. In this framework, black holes are tangles of strings, and information is preserved in their vibrations. Loop quantum gravity is another. It suggests space-time itself is made of discrete units, quantum loops woven together into a fabric. At the center of a black hole, where the singularity should be, the fabric reaches its limit and bounces back, creating a bridge to another region of space-time. There are others, theories involving higher dimensions, parallel universes, structures so strange they defy easy description. None of them are proven, none of them are complete, but they all agree on one thing. Black holes are not the end of the story. They're the beginning of a deeper one. Because if we can understand what happens at the event horizon, if we can resolve Hawking's paradox, we'll have learned something profound about the nature of space, time, matter, and information. We'll have glimpsed the rules that underlie the rules. And maybe that's the real mystery, not what black holes are, but what they reveal. They're not just cosmic vacuum cleaners, sucking up matter and light. They're laboratories. Natural experiments pushed to the most extreme conditions imaginable. Places where the universe shows us its limits, its contradictions, its hidden architecture. Every black hole is a question, and we're still learning how to ask. There's something almost poetic about it, that the darkest objects in the universe, the places where light goes to die, might hold the key to understanding everything. That the edge of oblivion might be the doorway to enlightenment. Or maybe it's fitting, because the universe has never been simple. Every time we think we've understood something, it shows us another layer, another puzzle, another horizon beyond which our knowledge falters. Dark matter, dark energy, the beginning of time, the silence of the galaxy. And now this, the paradox at the heart of black holes, the question of whether information can be destroyed or if it's merely transformed into something we can't yet read. We stand at the edge, looking in, trying to see through the darkness, and the darkness looks back, but it doesn't answer. Not yet. Because if space and time distort here, perhaps the laws themselves are only approximations of something deeper. Physics has built a cathedral. Over centuries, through the work of thousands of minds, we've constructed a framework that describes nearly everything. How particles interact, how forces propagate, how energy transforms from one form to another. We call it the Standard Model, and it's breathtakingly successful. It describes 3 of the 4 fundamental forces that govern reality. The electromagnetic force, which holds atoms together and makes light possible. The strong nuclear force, which binds quarks into protons and neutrons. The weak nuclear force, which governs radioactive decay and powers the sun. These 3 forces have been unified, woven together into a single mathematical framework. We can describe them with equations that fit on a single page. Equations that predict the behavior of particles to astonishing precision. We've tested these predictions billions of times in particle accelerators, in cosmic ray detectors, in experiments so precise they measure effects smaller than the width of an atom. And every time, the Standard Model passes, but there's a hole. One force stands apart. One force refuses to fit into the framework. Gravity, the force that holds planets in orbit, that curves space-time, that makes black holes possible, the force we experience every moment of every day, and we can't unify it with the others. It's not for lack of trying. Einstein gave us general relativity, a geometric description of gravity as the curvature of space-time. It's beautiful, elegant. It predicts black holes, gravitational waves, the expansion of the universe. Everything it says about gravity on large scales is correct, but it doesn't speak the language of quantum mechanics, and quantum mechanics doesn't speak the language of relativity. They're 2 different frameworks, 2 different ways of understanding reality, and at the places where they meet, where both should apply, they contradict each other. At the event horizon of a black hole, at the moment of the Big Bang, at scales so small that quantum effects and gravitational effects become equally important. We need something new, a theory of quantum gravity, a framework that describes gravity not as the smooth curvature of space-time, but as something quantized, discrete, built from fundamental units like everything else. This is the deepest unsolved problem in physics, and it's led to some of the strangest ideas we've ever considered. One of them is string theory. Imagine a particle, an electron, a quark, a photon. In the Standard Model, these are point-like objects, zero-dimensional, infinitely small, but what if they're not? What if, at scales far tinier than anything we can measure, particles aren't points but tiny loops, strings of energy vibrating at different frequencies? Just as a guitar string can vibrate in different modes to produce different notes, these fundamental strings vibrate in different patterns to produce different particles. An electron is one vibration, a quark is another, a photon is a third. And gravity? Gravity emerges from a particular vibration, a closed loop spinning in just the right way. The graviton, a quantum of gravitational force. In string theory, gravity isn't separate from the other forces. It's part of the symphony. One note among many, arising from the same fundamental strings that create everything else. It's a beautiful idea, but it comes with consequences. For the mathematics to work, for the equations to remain consistent, strings can't vibrate in just 3 dimensions of space. They need more room. 10 dimensions? Maybe 11? Where are they? The theory says they're curled up, compactified, rolled into shapes so small that we can't detect them. At every point in space, there are 6 or 7 extra dimensions, folded into configurations called Calabi-Yau manifolds. Structures so complex they exist at the boundary between geometry and art. We move through these dimensions without noticing, like an ant walking on a tightrope, aware only of forward and backward, oblivious to the circular dimension wrapped around the rope's width. And here's where it gets stranger. Gravity might be weak, not because it is weak, but because it's leaking into these extra dimensions. The other forces are confined to our three-dimensional slice of reality, trapped like patterns on a membrane, but gravity propagates through all dimensions. It dilutes, spreads out, which is why it feels so much weaker than electromagnetism or the nuclear forces, why a tiny magnet can overcome the gravitational pull of the entire Earth. Gravity isn't weak, it's just not entirely here. String theory offers other insights too. It suggests that our universe might be one of many, a bubble in an infinite foam of universes, each with its own set of physical laws determined by how the extra dimensions are curled. It proposes that black holes have entropy, a measure of disorder encoded on their event horizons. That information is preserved in the vibrations of strings near the horizon. It hints at connections between gravity and quantum mechanics so deep that space and time themselves might be emergent, not fundamental, not the foundation of reality, but consequences of something more basic. But here's the problem. We can't test it. The energies required to see strings directly are far beyond anything we can produce. The extra dimensions, if they exist, are too small to probe. The predictions string theory makes are often too vague or too distant to verify. It's mathematics, beautiful, intricate, internally consistent mathematics. But is it physics? We don't know yet. And so, other ideas compete. One of them is loop quantum gravity. It takes a different approach. Instead of asking what particles are made of, it asks what space itself is made of. In general relativity, space-time is smooth, a continuous fabric that can be stretched and curved and warped, infinitely divisible. But loop quantum gravity says no. Space is quantized. Just as energy comes in discrete packets called quanta, space comes in discrete units, tiny loops, braided together into a network, a fabric woven from threads so fine they exist at the Planck scale, 10 to the negative 35 meters. At that scale, space isn't smooth, it's granular, foamy, a flickering network of quantum geometries, constantly shifting, constantly reconfiguring. Time, too, is quantized. Not a smooth flow, but a sequence of discrete moments, frames in a cosmic film running at 10 to the 44 frames per second. We don't notice this graininess anymore than we notice the individual pixels on a screen. At the scales we experience, space and time appear continuous. But zoom in far enough, and the fabric reveals its texture. In loop quantum gravity, the Big Bang isn't a singularity, it's a bounce. The universe didn't emerge from nothing. It contracted from a previous state, reached a minimum volume determined by quantum effects, and rebounded. Before our universe, there might have been another. Black holes, too, are different. Instead of singularities at their centers, there are quantum bridges, regions where space-time reaches its maximum curvature and connects to another region, possibly another universe. The center of a black hole becomes a doorway. Loop quantum gravity makes predictions. It suggests that light from distant cosmic events might be slightly delayed depending on its wavelength, a hint of space-time's granular structure. It proposes observable effects from quantum geometry near black holes. Some of these predictions are testable, but like string theory, loop quantum gravity is incomplete. It describes space beautifully, but struggles to incorporate matter and energy in a consistent way. It doesn't yet explain how particles and forces emerge from the quantum fabric. We're still building, still searching. And there are other approaches, causal sets, where space-time is fundamentally discrete, a collection of points related by cause and effect. Asymptotic safety, which suggests gravity might be renormalizable after all, that the infinities that plague quantum theories of gravity might cancel out at high energies. Each offers a different vision of reality's foundation. Each suggests that space and time, the stage on which everything happens, might not be fundamental. Think about that for a moment. Space and time might be emergent, approximate, useful descriptions that work at our scales but break down at the deepest levels, like temperature. At the macroscopic scale, temperature is a fundamental property. You can measure it, feel it, build thermometers to quantify it. But at the microscopic scale, temperature doesn't exist. It's an average, a statistical property of many particles moving in random directions. Zoom in far enough, and there's no temperature, just motion. Space and time might be like that. Useful illusions that emerge from something more fundamental. A quantum network. Entanglement between degrees of freedom we don't yet understand. Information encoded in patterns we can't yet read. And if that's true, then everything we think we know about the universe rests on a foundation we haven't discovered. The cathedral we've built stands on invisible pillars. But maybe that's okay, because physics has always been about peeling back layers. Every answer reveals deeper questions. Every theory is an approximation, good within certain limits, waiting to be replaced by something more fundamental. Newton's gravity worked beautifully until Einstein showed it was an approximation of curved space-time. Einstein's relativity works beautifully until you reach quantum scales, where it breaks down. And whatever comes next, whatever theory finally unifies gravity with quantum mechanics, will eventually be replaced too, by something deeper, something stranger. There's no final theory, just an infinite descent into structure, pattern, and mystery. And maybe that's as it should be, because reality isn't a puzzle with a finite number of pieces. It's a fractal. The closer you look, the more detail you find. Complexity at every scale, patterns within patterns. We've learned that particles are made of quarks. Quarks might be made of strings. Strings vibrate in a fabric that might itself be quantized, built from loops or networks or something we haven't named yet. And beneath that, we don't know. But here's what strikes me as we dig deeper into the nature of space, time, matter, and energy. The universe looks less like a machine and more like mathematics, pure structure, pure relationship. Patterns that exist not in space or time, but as abstract forms that manifest physically. The equations don't just describe reality. In some sense, they are reality. The map isn't separate from the territory. The map is the territory. And if that's true, if the deepest layer of existence is mathematical structure, pattern without substance, form without matter, then what are we? We're patterns too. Configurations of matter and energy, organized in ways that allow us to perceive, to think, to understand. We're the universe looking at itself, mathematics becoming conscious. And that raises a question more fundamental than any we've asked so far. If the deepest structures of existence resemble thought, pattern, or code, then what of the thing that thinks, consciousness? We've traveled far, from the invisible scaffolding of dark matter to the first light of creation, from silent galaxies to the edge of black holes, from the quantum foam beneath space-time to the mathematical patterns that might underlie everything. But there's one mystery we haven't touched, the deepest one, the only one you experience directly, right now, in this moment, consciousness. The fact that you're aware, that you're reading these words or hearing them, and understanding what they mean, that there's something it's like to be you, an inner experience, a witness. Scientists can describe your brain. They can map its 100 billion neurons, trace the electrical signals racing between them, measure the chemicals flooding your synapses. They can tell you which regions activate when you see a face, hear music, feel pain, remember yesterday. But they can't tell you why any of it feels like something, why there's a light on inside. This is the hard problem of consciousness, and it might be the hardest problem there is, because every other mystery we've discussed exists outside us. Dark energy, black holes, quantum fields. We can study them at a distance, measure them with instruments, build theories that explain their behavior without ever experiencing them directly. But consciousness is different. It's the only phenomenon you can't observe from the outside. You can't point a telescope at it, can't trap it in a particle accelerator, can't measure it with any instrument except itself. You know, you're conscious because you are, but you can't prove it to anyone else, and no one can prove it to you. We're islands of awareness in a universe that, as far as we can tell, doesn't need awareness to function. The stars burn, galaxies collide, atoms bond and break, all of it following laws that make no reference to experience, to feeling, to the inner light of consciousness. So, why does it exist? One answer is that consciousness is what complexity looks like from the inside. Think about your brain. 100 billion neurons, each connected to thousands of others, forming a network of staggering intricacy. Information flows through this network constantly, patterns cascading, feedback loops reinforcing and inhibiting, the whole system humming with activity. And somehow, from all that complexity, awareness emerges. There's a theory called integrated information theory. It suggests that consciousness isn't a special ingredient, some unique substance or force. It's a property of systems that integrate information in specific ways. The more integrated the information, the more conscious the system. Your brain is deeply integrated. Every region communicates with every other, weaving perceptions and memories and thoughts into a unified whole. When you see a red apple, your visual cortex doesn't just process color and shape separately. It binds them together, integrates them with your knowledge of what apples are, your memory of how they taste, your decision about whether to eat one. The integration creates a unified experience. You don't see color plus shape plus memory plus decision. You see an apple, one thing, one moment of consciousness. And the theory goes further. It suggests that integration can be quantified, measured, that there's a number, phi, that represents how much consciousness a system has. A single neuron has a tiny amount. A network of neurons has more. A brain has vastly more. But here's the unsettling part. If consciousness is just integrated information, then it's not limited to brains. Any system that integrates information would have some degree of consciousness, a computer network, a cellular metabolism, even perhaps a sufficiently complex thunderstorm. Consciousness wouldn't be rare, it would be common, dim in most places, but present everywhere complexity arises. Your brain is just very good at it. Other scientists think consciousness might be even stranger, quantum. In the conventional view, the brain is a classical system. Neurons fire or don't fire, like switches turning on and off. The quantum effects happening inside atoms are too small, too fragile, to influence something as warm and wet as a brain. But some researchers disagree. They point to structures inside neurons called microtubules, tiny scaffolding made of protein holding the cell's shape. These microtubules, they argue, might be quantum computers, processing information not through classical switches, but through quantum superposition, where a system exists in multiple states at once until measured. If that's true, then every thought might be a quantum event. Your consciousness might arise from quantum coherence, entanglement between particles in your brain, states that exist in superposition until collapse by observation. And here's where it gets truly strange. If consciousness involves quantum mechanics, then the act of observation, the thing that collapses quantum superpositions, might require consciousness, which means consciousness wouldn't be a byproduct of the physical world. It would be fundamental to it. The universe couldn't exist in a definite state without something conscious to observe it. This is wildly speculative. Most neuroscientists are skeptical. The brain is too noisy, too hot, too chaotic for delicate quantum states to survive. Decoherence, the process where quantum superpositions collapse due to interaction with the environment, happens almost instantly in biological tissue. But we don't know for certain. And the questions it raises are profound. If consciousness is quantum, if awareness requires superposition and entanglement, then maybe it's not local. Maybe your thoughts aren't confined to your skull. Maybe consciousness is distributed, woven through the quantum fabric of space-time itself. Maybe minds can influence each other in ways we don't understand. Not telepathy in the mystical sense, but something emerging from quantum correlations, connections that transcend the usual boundaries of space and time. Or maybe the truth is even stranger. Maybe consciousness isn't emergent at all. Maybe it's fundamental. This is panpsychism, the idea that consciousness isn't something brains create, but something that exists at the most basic level of reality. Every particle, every field, every quantum of energy might have some primitive form of experience associated with it. Not thoughts, not awareness in the way we understand it, but something. A faint glow of subjectivity, a minimal interiority. When matter organizes into complex structures, these tiny flickers of consciousness combine, integrate, amplify. A neuron has more than a single atom. A brain has vastly more than a single neuron. Consciousness builds. In this view, you're not creating awareness, you're concentrating it, gathering it from the universe and focusing it into something bright enough to recognize itself. It sounds mystical. Maybe it is. But it solves a problem. If consciousness is fundamental, then we don't have to explain how it emerges from non-conscious matter. We don't have to cross the explanatory gap between neurons firing and the felt quality of redness, the taste of salt, the ache of grief. It's already there, woven into the fabric of existence, waiting to be organized. And there's something almost beautiful about that idea, that the universe isn't dead matter moving through empty space, that there's a kind of interiority to everything, that rocks and rivers and stars have some vanishingly small measure of experience, and we're just the places where that experience becomes concentrated enough to look back at itself. We're the universe waking up. But here's the question that keeps me awake at night. If consciousness is fundamental, or emergent, or quantum, or some combination we haven't imagined yet, what does that mean for everything else we've discussed? What does it mean for the nature of reality? Because consciousness does something no other physical system does. It turns information into meaning, data into understanding, patterns into purpose. When you look at the night sky, photons strike your retina. Electrical signals cascade through your visual cortex. Information is processed, patterns recognized. But somewhere in that process, it becomes more than information. It becomes wonder. The photons carry no intrinsic meaning. The atoms in your brain have no goals, no desires, no sense of beauty. And yet you feel something when you see the stars. Awe, curiosity. A sense of your own smallness against the vastness of space. Consciousness transforms matter into mattering. And if consciousness is woven into the universe, not separate from it, but part of its fundamental nature, then meaning isn't something we impose on a meaningless cosmos. It's something the cosmos generates through us. We're not observers standing outside reality, looking in. We're how reality observes itself, how it knows itself, how it creates meaning out of the raw material of existence. Every thought you have is the universe thinking. Every emotion you feel is the universe feeling. Every question you ask is the universe asking itself what it is, why it's here, what it all means. And maybe that's the answer to Fermi's paradox, or at least part of it. Maybe consciousness is rarer than we think, not because life is rare, but because awareness requires such specific conditions, such precise organization of matter and energy that most of the universe never achieves it. We might be precious not because we're alive, but because we're awake. Or maybe we're not alone. Maybe consciousness appears wherever complexity reaches a threshold. Maybe the universe is full of minds, scattered across galaxies, experiencing reality in ways we can't imagine. Silicon minds and artificial networks. Quantum minds and systems we'd never recognize as alive. Collective minds spanning entire planetary biospheres. Thoughts moving at geological speed. All of them mirrors. All of them reflecting some aspect of the cosmos back to itself. And here's the deepest question. If consciousness is how the universe knows itself, does that mean the universe needs consciousness? Is awareness playing some essential role, something beyond mere observation? Some interpretations of quantum mechanics suggest yes, that the universe exists in superposition, all possible states at once, until consciousness collapses the wave function, choosing one reality from infinite possibilities. We're not just observing, we're creating. Every measurement, every observation, every conscious moment is an act of creation, collapsing possibility into actuality. The universe dreams all possibilities, and consciousness makes them real. It's a staggering thought. And maybe it's wrong. Maybe consciousness is an accident, a quirk of evolution, no more fundamental than the pattern of veins in a leaf. But maybe it's not. Maybe awareness is written into the laws of physics in ways we haven't discovered yet. Maybe the equations that describe reality include terms we're missing, variables that account for the inner experience of being. Maybe solving the hard problem of consciousness will require rewriting physics from the ground up. Or maybe consciousness and cosmos are two sides of the same thing, matter and mind, physics and phenomenology, the objective and subjective faces of a single underlying reality. We don't know, but we're asking, searching, building theories and conducting experiments, trying to understand how 3 pounds of matter inside our skulls can generate the entire theater of experience. And in the meantime, we're here, conscious, aware, capable of wondering about our own wondering, which is, when you think about it, extraordinary. The universe spent billions of years assembling atoms into stars, stars into planets, planets into conditions where chemistry could become biology, biology could become complexity, and complexity could become us. Beings capable of looking back at that whole process and understanding it, feeling it, marveling at it. We're stardust that learned to think. Carbon and oxygen and nitrogen arranged just so, humming with the energy of ancient suns, organized into patterns intricate enough to be self-aware. And if that's not magic, it's close enough. So, as we drift toward sleep, toward the place where consciousness dims and dreams take over, remember this. You're not separate from the cosmos. You're a part of it. A way for the universe to experience itself from the inside. And right now, in this moment, you're the mirror through which reality sees its own face. If the universe knows itself through us, what else might it be dreaming? We've reached the edge, not the edge of space, because space might have no edge, not the edge of time, because time might loop back on itself or branch into infinite paths, the edge of what we can know. Beyond here, the territory becomes uncertain. The maps dissolve into speculation. The questions grow so large they swallow their own answers. This is level 95. And the question is simple, terrifying, magnificent. What if our universe isn't the only one? What if everything we've discussed, every galaxy, every star, every atom from here to the cosmic horizon and back, is just one bubble in an infinite foam, one universe among countless others? This is the multiverse. And it's not science fiction. It's a serious proposal emerging from our best theories, from inflation, from quantum mechanics, from string theory, from the simple mathematics of probability stretched to its limit. Let's start with the simplest version. Cosmic inflation. That moment right after the Big Bang, when space expanded faster than light, doesn't have to stop everywhere at once. It can end in some regions while continuing in others. Where it ends, a universe forms, a bubble with its own space, its own time, its own physics. And inflation keeps going outside that bubble, spawning more bubbles, more universes, endlessly. Eternal inflation. A process that, once started, never fully stops. New universes budding off from the inflating space like soap bubbles forming on an infinite surface, each one expanding, cooling, forming galaxies and stars, perhaps even life. Our universe is one bubble, and there's no reason to think it's the only one. But it gets stranger. If the multiverse is infinite, and if the laws of physics allow for variation between universes, then every possible universe exists somewhere. Universes where the constants of nature are slightly different, where gravity is stronger or weaker, where electrons have different masses, where the expansion rate is faster or slower. Most of these universes would be sterile, hostile to complexity. In some, matter wouldn't form at all. In others, it would collapse immediately into black holes. In still others, stars might never ignite, leaving cold clouds of hydrogen drifting forever in the dark. But somewhere in that infinite expanse, there are universes like ours, and somewhere there are universes almost like ours but different in tiny ways, where you made a different choice this morning, where history unfolded along a slightly different path. And if the multiverse is truly infinite, then there are universes identical to ours, down to the last atom, down to the last thought in your head right now. Infinite copies of you, reading these words, thinking these thoughts, wondering if they're alone. This is the many worlds interpretation of quantum mechanics taken to its logical extreme. In standard quantum mechanics, a particle exists in superposition until measured, multiple states at once. And when you measure it, the superposition collapses into one definite outcome. But what if it doesn't collapse? What if every possible outcome happens, but in separate branching universes? When you measure a particle's spin and find it pointing up, there's another universe where you measured it and found it pointing down. Both outcomes are real. Both universes exist. You just happen to be in one of them. Every quantum event, every moment where probability splits into multiple possibilities, creates a branching. The universe divides, multiplies. And it's been doing this since the beginning. 13.8 billion years of quantum events, each one branching, creating new timelines, new histories, new versions of reality. The number of universes in this scenario is beyond comprehension. More than all the atoms in our observable universe. More than all possible thoughts. An infinity so vast it makes infinity look small. And you exist in all of them, or at least in the ones where conditions allowed you to exist. Living slightly different lives, making slightly different choices, experiencing slightly different versions of this moment. Somewhere, you decided not to listen to this. Somewhere, you never existed at all. But here, now, you're here. And that raises a question. Why this universe? Why are the constants of nature so precisely tuned to allow complexity, stars, planets, life, consciousness? The strong nuclear force is just strong enough to hold nuclei together, but not so strong that all hydrogen have fused immediately after the Big Bang. The electromagnetic force is balanced perfectly to allow chemistry. The cosmological constant, the energy of empty space, is small enough that the universe didn't tear itself apart before galaxies could form. Change any of these values by even a tiny amount, and the universe becomes uninhabitable. This is fine-tuning. And it's troubling. One explanation is design, that the universe was crafted deliberately with life in mind. But that raises more questions than it answers. Who did the crafting? Why? And where did they come from? Another explanation is luck. We exist in a universe that allows us to exist. It's tautological, but not meaningless. If only one universe exists, and it happens to have the right properties, then we're just incredibly fortunate. But if the multiverse is real, the explanation becomes simpler. If there are infinite universes with varying constants, then some of them will have the right conditions for life by pure chance. And naturally, we find ourselves in one of those universes, not because it was designed for us, but because we couldn't exist anywhere else. This is the anthropic principle. We observe a life-friendly universe not because all universes are life-friendly, but because observation requires observers, and observers require specific conditions. It's selection bias on a cosmic scale. You don't marvel at winning the lottery if everyone who exists is a lottery winner by definition. But there's a deeper, stranger interpretation. What if consciousness plays an active role? What if the universe doesn't just allow observers, but requires them? Some interpretations of quantum mechanics suggest that observation collapses possibilities into reality, that the universe exists in superposition, all possible states at once, until consciousness looks at it and chooses one. If that's true, then the universe can exist without consciousness, and consciousness can exist without the right universe. It's a loop, a self-referencing paradox. The universe creates consciousness, and consciousness creates the universe. Neither comes first. Both require each other. The cosmos is participatory. Reality is a collaboration between matter and mind. And if the multiverse is real, then maybe consciousness selects which universe it inhabits. Not deliberately, not consciously, but through the simple fact of existing. You're here because here is where you can be. And that thought, more than anything else we've discussed, sits at the boundary of science and philosophy, the place where equations meet meaning, where observation meets interpretation. We can write the math, we can describe the branching, the inflation, the quantum superpositions, but what it means, that's still open, and maybe it always will be. Because here's the uncomfortable truth. We might never know if the multiverse is real. If other universes exist beyond our cosmic horizon, separated from us by distances so vast that light will never cross them, we can't observe them. We can't measure them. We can't test their existence directly. They're beyond the reach of science, not because we lack the technology, but because the structure of space-time itself prevents contact. Other universes, if they exist, are causally disconnected from ours. Information can't flow between them. Influence can't cross the boundary. They're real, perhaps, but unknowable. And that forces us to ask, what does it mean for something to be real if it can never be observed? If no experiment can confirm or deny it? If it makes no difference to anything we can measure? This is the problem of unfalsifiable theories. The multiverse, in its strongest forms, isn't a prediction. It's a consequence of theories designed to explain other things. Inflation, quantum mechanics, string theory. These theories work. They make testable predictions about our universe, and the multiverse comes along as a side effect, an implication we can't avoid if the theories are correct, but we can't confirm it. We're left with inference, indirect evidence. The fact that the theories which predict a multiverse also explain things we can observe, the fine-tuning of constants, the patterns in the cosmic microwave background, the behavior of particles at quantum scales. Maybe that's enough, or maybe it's not. Maybe the multiverse is real and we'll never know. Maybe we're surrounded by infinity and forever trapped in our single bubble, unable to see beyond the walls. It's humbling, and it's appropriate, because the more we learn about the universe, the more we realize how much we don't know, how much we can't know, how much might be forever beyond the reach of human understanding. 95% of the cosmos is dark matter and dark energy, substances we can't see, can't touch, can't directly detect. We know they're there because of their effects, but their nature remains mysterious. We don't understand consciousness, don't know how awareness arises from matter, can't explain why there's something it's like to be alive. We don't know what happened before the Big Bang, or if before even makes sense. Don't know if time had a beginning, or if it stretches infinitely backward. We don't know if we're alone in the universe. Don't know why the galaxy is silent. Don't know if intelligence is common or rare, precious or ordinary. We don't know if information is truly preserved in black holes, or if it's destroyed in ways that violate quantum mechanics. Don't know what lies at the center of a singularity where our equations break down into infinities. We don't know what quantum gravity looks like. Don't know if space is smooth or granular, if time is continuous or discrete, if reality is strings or loops or something we haven't imagined. And we don't know if other universes exist, don't know if the multiverse is real, and probably never will. The unknowns outnumber the knowns by an incomprehensible margin. And maybe that's the point. Maybe mystery isn't a problem to be solved. Maybe it's a feature, not a bug, the universe's way of staying interesting, of ensuring there's always another question, another horizon, another deeper layer to explore. Every answer we find opens new doors. Every mystery we solve reveals others waiting behind it. The structure goes down forever, complexity upon complexity, pattern upon pattern, with no bottom, no final answer, no ultimate explanation that ties everything together into a neat bow. Reality is inexhaustible. And there's something beautiful in that, because it means we'll never run out of questions, never reach a point where there's nothing left to wonder about, never stand at the end of knowledge and find it empty. The universe is infinite in depth, and we're part of it, made from it. shaped by it, capable of exploring it one question at a time, one discovery at a time, forever moving toward an understanding that recedes as we approach, like the horizon that expands with every step. Mystery is the universe's final language, the grammar of existence, and we're fluent in it, whether we know it or not. Because to be conscious is to question, to wonder, to stand in awe of the vastness and strangeness and improbable beauty of it all. You are made of stardust, organized by physics, animated by chemistry, aware because of processes we barely understand. You exist in a universe that might be one of infinitely many, shaped by constants that might vary elsewhere, governed by laws that might be approximations of something deeper. You're surrounded by dark matter you can't see, dark energy you can't explain, a cosmic horizon beyond which information can never reach you. You're conscious in ways science can't fully account for, alive on a planet that might be common or might be precious, intelligent in a galaxy that's either teeming with minds or hauntingly empty. And you're falling asleep, drifting into dreams where the rules bend and break, where time loops and folds, where you can be in two places at once, where consciousness slips free from the constraints of waking reality and explores landscapes that exist nowhere but in your mind. Maybe sleep is practice, a nightly rehearsal for the multiverse, a reminder that reality is stranger, more fluid, more layered than it seems. Or maybe it's just what happens when a brain needs rest. Either way, you're here, now, in this universe, in this moment. And the cosmos, vast and ancient and full of secrets, continues its slow dance through time. Stars burn, galaxies turn, black holes evaporate, space expands, quantum fields fluctuate. And somewhere, in all that immensity, you exist, asking questions, seeking answers, wondering what it all means. And maybe that's enough.